you. Well, thank you everybody for coming. I know these starts are like very, very busy at the end of the semester. So I belong to the Intelligent Transportation Systems Group, the Strata Center for Robotics. These should be here. And today I'm just going to give a talk about like an overview of what we do. It's not going to be very technical. It's more like high level understanding of what we're doing at ACFR. So first, just a little bit of an introduction of the center. So we are part of the Faculty of Engineering. We're a center that we do a lot of things on robotics. It used to be called Strata Center for Field Robotics, but then we removed the field, and now it's just robotics in general, and that's because the center itself wants to do more research in other areas in robotics, not only things that can go to the field. So there we have different kinds of groups there. We have, for example, people that are in charge of doing mining. They have huge projects with Rio Tinto. We have people doing agriculture. Most of you might have known Salah. He's heading that group, very successful. We have also the marine robotics with Stephan Williams. And we have these different robotics in general. We have people that are working on robots that can walk. We have people working on robotics that can bend, and we're working on intelligent transportation systems. So our research is divided in 3 parts. Let me just see if I can get it. Oh, this is another one. So research is divided in 3 parts. One is the intelligent vehicle and smart infrastructure. The other one is building data sets for data analytics and AI. And the last bit is digital twins, human factors, everything related with human-machine interfaces for autonomous driving. So the first thing is which capabilities we have. So we have 2 of these small vehicles. These vehicles are equipped with different sensors like Lidars, cameras, compute system that we can use to perform self-driving around Chippendale. And we cannot do it outside of Chippendale because we don't have permission to do it. It is very, very tricky to get permission in order to be able to have these cars driving by themselves. Especially, it requires a lot of paperwork with transportfolios of wells, a lot of we need to have a lot of permissions. Insurance is one of the things that are very tricky with this. You dealing with this kind of vehicles because they tell us, okay, so you have expensive equipment, but how can I know this? It's safe, like how safe it is. So you have. It requires a certain level of safety, and I will explain that in a bit. So we have these 2 vehicles. They are exactly the same vehicle, so we can use it, for example, if we want to interact with each other. We have LiDAR cameras. We don't have radars here, but we have very specialized equipment in these cars. We also have an urban vehicle. And this one is slightly better in the sense that we can collect data wherever we want because it's just a normal vehicle that we can drive around New South Wales. And we have used it quite a bit for different projects. We have 1 LiDAR on top, and we have 6 LiDARs around the vehicle. These small LiDARs that you see here are basically used for blind spot detection. We have also a radar. We have 8 cameras. I will show you some videos that we have collected with this car. We also have something that you cannot see here, and unfortunately, it's a roadside unit that is located on this pole. This roadside unit, we use it to monitor this intersection. And if you have ever walked from here to Central Park Mall, you might have crossed this intersection. This is just here in Chippendale, very close to where we are in J18. So this is Abercrombie Street, and this is Myrtle Street. We have this roadside unit broadcasting different kind of information that I will talk during this presentation. And we have many VR headsets that we use to have or to perform experiments about interfaces with pedestrians, for example, interfaces from the vehicles to communicate something to the people who are crossing the street. So the first part is demonstrated intelligence. So like I said before, we do two things. One is with intelligent vehicles, the other one is with special infrastructure or roadside unit. Let me just show you a short video here. This is some of the, this is just, sorry, a demonstration that we have done around Chippendale. So what you see here is just someone say, okay, we're going to this position. We want to go to buy fried chicken, for example. So the car goes by itself, so nobody's actually driving the vehicle. And you cannot see properly here because I think of the lighting, but we have created high definition maps in order to navigate this roundabout and this intersection that you're about to see. So the first thing is we need to know where we are. So the maps are created. There are two types of maps that we run here. One is pure localization. So we run a SLAM algorithm around the area where we want to drive, and we use that as a reference. Once we want to localize the vehicle, we just have to compare the point cloud that we have at the moment against that specific map and get an estimate of the position of the vehicle. The other map that we have is, and I will, maybe not in this route. The other map that we have is an HT map or a map of the routing of the road. And that's very important because obviously there's some regulation, there's some lane markings that we need to follow in order to drive successfully. For example, here we arrive to our destination, which is the fried chicken place in Chippendale. So now we say that, you know, we need to go to the next stop. With the LiDAR, we not only do the localization, but also we do object detection. So you will see that, for example, the car actually stops when it sees an obstacle in front of it. The thing is here in this video that you see, we don't have a lot of cars coming to us or a lot of pedestrians. And that's one of the reasons why we got the permission to drive by itself there. If it were like something very, very crowded, we might not have got permission. It is very tricky to handle this kind of permissions with Transport for New South Wales. Another thing that you can see probably here, and maybe I just stop. When the vehicle is approaching the intersection. I'm gonna start it again. Oh, no. Let me just try again. This before. I just need to stop it in the right place. When the vehicle is approaching the intersection, you can see the traffic light appearing on this screen. Can you?
You can put the values.
Not that great.
Second ago, I saw it.
There you have. There, it's very, very small. So what we're doing with the roadside unit is transmitting information of the traffic lights to the vehicle. So the roadside unit is actually, at the moment, is transmitting two things. One is the phase and the signals of the roadside, of the traffic lights. And the other one is a message called map and message, which tells you what is the topology of the intersection. With that topology of the intersections, we can actually know where we are in that intersection to plan where we're going in future. And obviously with the information from the traffic light, we know if we need to stop, we know if we can go ahead, etc. Now you're going to see something. Someone is going to do something on the screen. So someone press something. And it's not because we are doing something tricky, but because we need to make sure that it's safe to go ahead. So this is one of the safety layers that we need to have in these vehicles in order to operate in the real world. So they need a human in the loop. Once we're in the intersection, we want to turn right, turn left, go straight. We need to have someone saying, yes, confirming, yes, it is safe for you to do, for you to do so. So that was that person that clicked something on the screen.
Are they being prompted with audio to do that?
We don't have audio at the moment. These are EVs. For some experiments that we did, we had to put like a buzzer, like going just to people to know that it was there, but
No, I
nothing.
mean, the person who pressed the button, how were they prompted that the vehicle needed a button press?
oh, well, because there was something happening in this on the screen. And also because we know we are the ones that operate everything. So we know what we have to do and when we have to do it. We're like, the problem here is that you're not allowed, for example, you are not allowed to operate this vehicle. Has to be specific people who have been trained in order to operate it.
Yeah, I just meant more like if you come up to an intersection, the person sitting there knows that they should be prompted. So they're checking them in advance and then they can press it. But I think the interesting thing is, does the vehicle ever, like, the vehicle first should say, I think it's safe, is it?
Yes,
You
yes,
know, and so like, you have to wait until you're prompted to press it.
yes. So in an intersection, you always have human in the loop, always. But obviously we have sensors that can tell you there's a car coming, there's a pedestrian crossing. And if that happens, the car is not going to start, it's not going to start moving. So this is just like a second layer that we have there. And we have been doing this kind of experiments for quite some time already in Chippendale. You can see different kind of loops that we do around the same area. Let me just show you what is happening. Maybe if you can see in this one better what happened on the screen. Okay, probably here it is easier. Here appears like the face of someone. This is the previous person who was in charge of this vehicle. So it said, is it safe to cross? And then the person who's operating the vehicle has to validate if it's safe or not. But you see, at the moment the car is able to stop for a car that is in front, is able to stop for a person who's crossing the street. We have done plenty of these experiments. At the moment, this is not a very fancy car. This is not a car that you can go to any intersection. You can go inside of the city of Sydney and run it by itself. There are plenty of things that have been manually tweaked in order to operate it in this area. This is a very hard problem to solve it. That's what you see. That's why we don't have self-driving cars running everywhere. But these are just not only for our experiments, but also to run things that students, for example, want to implement. One of the things that we do is perception. Perception is how the car can see the environment. For that, we use usually cameras and lidars. We have some radars, but we don't use it that much. They're quite noisy. The lidars and the cameras can give you a lot of information on what is happening around. Cameras are very good because they give you information about color, they give you information about shape, they give you information about texture. So a lot of features that you can extract using some machine learning techniques in order to do object detection, to do object segmentation. And that is actually very valuable just for us to know what is happening around. LiDARs, on the other hand, they are very good at giving us 3D information, giving us what is the depth, how far is that car, where we are in the environment. If we combine it, for example, with a point cloud map. So what we do usually is combine these two types of sensors. want to do, for example, here, object detection, we were doing it with camera. And then we combined that with LiDAR. So we had what we're seeing and how far it was, what we were seeing. And let me just run this very quickly. This was an experiment that we had, I would say probably a few years ago, maybe 3 years ago, that we were running that in order to build the first version of a roadside unit. So the detection is being actually done with the camera. We were using just a basic YOLO detector, but because we had calibrated the camera on the LiDAR, we are able to do the detection and tracking of the vehicles in that intersection. Same here, we have collected a lot of data around the University of Sydney. So you might have found yourself maybe in one of those videos where this one was collected in Easter Avenue, and we were doing some work on pedestrians. So we're doing detection, tracking, and prediction of pedestrians. This work actually has been quite successful, has been probably the work that has more citations of the group, because calibration is a very complex problem. It looks very easy just to know where things are with respect to each other, but getting features, getting the correct position of one sensor with respect, for example, the cameras with respect to the LiDAR, it is a very high dimensional problem. And this one is a video of the roadside unit that we have in Chippendale now, the one that is operating at the moment. We have two LiDARs. We have one that is a dome LiDAR that it is more like a cone. So it goes from top to the bottom running, and the other one is just a normal LiDAR that is a rotational LiDAR, horizontal. These LiDARs were also the same thing, calibrated, so we can see the same things at the same time. There are two things that we are publishing. One is the pattern information, like I explained before, the map information of the intersection, and the pattern, which is the signal phase and timing of the traffic light. We can broadcast that information, and we can receive it from the EVs, and we can receive it also from the other car, which is the urban vehicle. And the idea with this project is for us to broadcast something called CIM, Cooperative Awareness Messages. So we can run something here, like a object detector, 3D object detector, and then translate that into a global reference frame that we can send to the vehicles. And because the vehicles, they themselves, they have the localization algorithm, they know, they said, this car is within 3-4 meters of where my predicted path is going to be. And it's very interesting because if you can see here, we have cars coming, very heavy traffic from Abercrombie Street, but we also have pedestrian path, and we have a bike lane, which actually allow us to collect more data and to create data sets that are more focused on vulnerable road users instead of just cars. This project actually finished last year. So the idea here was just to use it as a pilot for Transport for New South Wales, because this was a project between Transport for New South Wales at the University of Sydney of seeing what are the capabilities that we can develop in order to communicate a roadside unit with vehicles. How can we increase safety, for example? We have done advanced roadside installation, which you might think that is very easy, but it requires so much regulation. It requires so much paperwork, a lot of bureaucracy to do anything on the street. Autonomous operations at the intersection, red light evaluation warnings. So we are also able to create some warnings for the vehicles and warn for pedestrians in like when they're in blind spots. I will show you just a video. Probably this one is better than the other one in terms of what you can see here. We have the countdown that it comes from the traffic light itself. So it tells us if we can proceed or not. And I don't have the other one. Let me see. Let me see if I can find the other one. Probably it's in another slide. So this is one of the projects that we finished recently, and this project also we finished at the beginning of this year. So we want to use roster units for something different. We not only for intersection. So for this specific project, we work with the equivalent of transport for New South Wales, but in Queensland. So I will have a question for you. But you might know what is the most dangerous bird in the world? The cassowaries, yes. Usually when I give this talk somewhere else, like no street or something like that. Exactly. The cassowaries are the most dangerous birds in the world. But also they are, their population is reducing drastically. And that's mainly because, you know, we humans were building roads, where we are building, we're building houses in their protected area. So it is a shame that these very beautiful animals are now an endangered species. They are not very aggressive, and the attacks are very rare, but if you try them, they can be deadly, right? So like I said before, they're endangered species, and because of many things, right? Like habitat loss, a lot of cassowaries are on the streets in Queensland, North Queensland, very close to Cairns, and they get hit by cars. And obviously they can be dead or they can get injured, which is something that we don't want. We don't have a lot of cassowaries in the world. You have cassowaries in Australia and Papua New Guinea, and we don't want this to happen, right? And the idea with the roadside unit was to detect the cassowaries, right? Another thing is a safety problem. So when we have an animal that you're driving and you have an animal crossing the street and you are not fully aware that what was happening, you might do like something crazy. You can create a mayhem if something happens there. I think it is very important that we can inform drivers that there's an animal, an endangered species that is happening, that is crossing the road. So what happened with the roster unit? So one of the things that we wanted to do was use AI techniques in order to detect the cassowaries within certain amount of space from the vehicles. We said that it's going to be 200 meters. Then we're going to, once we detect the cassowary, we're going to alert them using a VMS, telling them there's a cassowary, reduce your speed. And we want also to know if we can actually influence the driver's response. So if the driver is actually reducing the speed, so the less cassowaries are going to be in the hurt. We were in charge, especially of this small part, which is the AI technique. We had another team in Queensland doing the second and the third part. And there were many constraints, very different from what we have, for example, in the lab, that we have a lot of compute, we have a lot of resources. When you are working in the rainforest in Queensland, you don't have a lot of these resources. So we talk about the power. The power was coming from solar cells. That was not enough for a very expensive, a very powerful computer. So we had to use the smallest NVIDIA machine that we could get. Also, the sensors that require quite a lot of power. We had here a Lidar that at the end we had to just turn it off because there was not enough power to make it work. So there were a lot of constraints. The other thing is you don't have internet connection there. You just need to have something with the SIM card. And if you wanted to transmit data from there to Sydney, it is going to be quite expensive because we have HD cameras, we have a lot of point clouds. And imagine these cameras are working 24/7. Another thing that was very challenging for us was, where are we going to get object detectors for cassowaries? We don't have a cassowary data set. If you have ever done something with YOLO detection or AI sort of detection, they are not cassowary data sets, especially for this kind of applications. What we did first was we said, okay, we're going to install the cameras there, we're going to collect data, we're going to annotate this data, and then we're going to train the detector. So what happened? We only accumulated 3 minutes in the first weeks. So that was very worrying because obviously we need to deploy everything because we had our industry partner very worried about that. And also, like I said, transferring data is quite expensive. Can you spot the cassowary? This is an image, for example, from the cameras that we were using. And the cassowaries were just very small. So that also means that we had to change the lens of the cameras, the position of the roadside unit. Another thing is this ground was very unstable. And whenever we positioned the roadside unit correctly, over time, it was just moving. So there are a lot of challenges when it comes to implementing things in real life. So we said, okay, we want to do something smart about this. So we use VLM in order to do the detection from now on. And this is a visual language model that now are very popular. We use SAMD, which is a segment anything methodology for segmenting anything. And we use Gaussian blending for data augmentation. So I will show you exactly how it works. We actually deployed as YOLO V8, which is very fast. So it was very easy for us to train it and also to implement that in the video machines. You cannot use. You cannot see anything. Okay, I think it was just the PowerPoint. So the question here was, okay, so we're going to use a visual language model that has been already pre-trained. So there are a lot of things that are already learned in these pre-trained VLMs. One is the word cassowary, it's not there, but then we do what we do all the time. Whenever we don't understand something, so we just ask ChatGPT, right? So we ask ChatGPT, tell me 2 or 3 animals that closely resemble cassowary visually. So it says, okay, you can detect an emu, an ostrich, and there was another one that I don't remember what was the one. So we decided just to use labels as emu and ostrich using the camera images that we were obtaining. Then we also asked ChatGPT for attributes. We said, okay, can you give me some attributes like color or shape of the cassowaries? So one of the colors is, for example, blue, another color is black. So we combine all these words, and we input that into a visual language model. So at the end, we were asking the visual language model, can you detect blackbirds? Can you detect a blue ostrich? Can you detect a black emu? So we use this combination of prompts with the images that we're obtaining from the camera. And the VLM actually gave us the bounding boxes for the bird. And this is only true if you don't have black emus and blue ostrich at the same time. The advantage of that area, the specific area, that the only bird that you could see was the the cassowary. So then because we had so many bounding boxes around that, we just apply the non-maximum expression algorithm just to get one single bounding box. And after that, we use SAM. SAM is just an algorithm that is used nowadays just to detect the animal that is in there. So by using SAM, we could just obtain the shape of the cassowary. Then we had images, a lot of images, more than what we wanted, of just background noise, like just background. So we added this into the image using Gaussian blending, and we created a huge data set from there. So we just detect the animal, using VLMs, some to do like a data augmentation data set. And with that, we started training the YOLO detector. So how it works was yes.
Can you go to Zoom and take pictures?
We use pictures of the cassowary, yes, from the zoo or from the internet, and we use it for doing the data augmentation. So this image is not only from that roadside unit, but images from the internet.
But can you generate using like what's called like using like synthetic data or generate?
Yeah, it doesn't work that well. It doesn't work that well. At least when we started doing this, it did not work well. Because it was too different from the data that we were obtaining from the field. So the first stage was just to create this synthetic data. So we initialized the model. Then we had a very, very low threshold for detecting the cassowaries. So we collect false positives, true positives for a couple of weeks. Then with all these detections, those were the only ones that we were transmitting to Sydney, because we cannot transmit everything 24/7. It was impossible to do so at that stage. Then we label things again. There were some part that we had to do hand label because, yeah, VLM couldn't do everything at that stage, but VLM actually helped quite a bit in doing the auto labeling pipeline. And then we retrain the model, and then we check that again. We collect more data, we label the data again, and then we retrain. And this was happening, it happened for a couple of months. And this is an example of the final version of the detector working in that intersection, in that road. So you have the cassowary going, crossing. We had different domains in the sense that we were using it for detecting cassowaries during the day, and during the night we were using also infrared cameras, and that actually helped us quite a bit in order to detect more cassowaries. So you see that at the end it worked quite well for detecting the animal. So at the end, this is one of the images at nighttime. We were detecting the animal. We were using two YOLO detectors, one for the infrared camera, one for the RGB camera. We put it through the NVIDIA machine, and then we have added sign saying cassowary detected and slow down. The other team, and I was talking about what people from Queenstown were doing, they had this area that was the area of interest. And we have the roadside unit located in this area. And the traffic, we have traffic direction going from the left to the right. And we have some tubes. And these tubes, we use them for detecting changes in speed of the vehicles. And that's just because we want to know exactly if the sign that we were displaying was causing something in the behavior of the drivers. You can see here, there's a cassowary crossing. Then we're saying, okay, there's a category, you have to slow down. Cars slow down. The category crosses the street safely, and the vehicles are also going safely. This was an experiment at the beginning of the year. Now, we were quite happy with it. Another thing that we do is solving a lot of problems with data. We create data sets for autonomous cars, and we apply a lot of machine learning techniques in order to do things with perception systems and data analytics. So data sets are actually on the multi-letters have changed quite a bit, but it's okay. You have to forgive me about it. So why are they so hard to make? One is few research groups actually around the world have the capabilities to collect this amount of data. One is not only the equipment that is extremely expensive, but also you need to have someone who's an expert synchronizing the sensors. Synchronizing the sensors itself is a very hard task. Calibrating the sensors. Collecting the information is not easy. We have had a lot of issues with the computer's I/O, input-output, where we can generate all the data, but we cannot store the data at the same time. So we had a lot of frames being dropped, and it is very tricky. So it's very resource intensive, and also it's very, very expensive. We focus on different areas when we collect the data. One is uncertainty. The other one is using multiple sensor modalities, calibration, and all the information needs to be synchronized. Otherwise, but there's not much use. This was the first data set that we not playing. Well, it's not playing. I'll have to send the video later. But this was the first data set that we collected around the University of Sydney with these small cars. And we drove every single week for over a year collecting data. And what was the intention of this data set? One was to capture different weather conditions, different illumination conditions, different structural changes. This happened when we had, I don't know which building was that, close to engineering, there was a building that was fully demolished. That was just before COVID. So we wanted to capture this kind of changes because, especially when you create a map, changes in the environment can actually damage the localization algorithms for the vehicles. Then we started creating some other new data sets with a more fancy equipment. Like I explained a little bit before, we had, for example, here a radar, we have few lidars. Let me just. And we have the cameras. We have 8 cameras. So we have cameras that are 60 degrees and 120 degrees field of view, especially for the front, on the front part of the car. And that's mainly because you want to know 2 things. One is what is close to you, and the other one is to have a holistic representation of the environment. And this one is some of the information that we have captured. Here we have 2 front cameras. One is 120 degrees field of view, and the other one is 60. Normally, you use the 61 to get very fine-grained detections, for example, traffic lights, if you're using just camera information. And this one is just to have a holistic overview of what is happening in front. These are the side cameras, and then we have back cameras also to cover 260. And the LiDAR is on top, so the LiDAR actually covers 360 degrees. And we have done also a lot of work on getting semantic information from the camera images. Usually you have some data sets that have been released Now, they're very famous, but they have been all collected in countries like Germany, in the US, in Singapore, but nothing much happens in Australia. We're quite isolated country when it comes to this kind of technology. So we have, oh, this is what I explained. So these are, for example, the results that we obtain when we try to get semantic information. Okay, when we try to get semantic information using the cameras that we using, the cameras that we have been using for collecting data. So you see that there's a lot of degradation of the semantic information. So what we did is we created something called Cityscapes, which is a data set of semantic panoptic information around New South Wales. This is also a project that we had with Transport for New South Wales in order to incentivize people to do more research in Australian environments. We also had another one called M2S road, where we want to check which are the damages on the road in New South Wales. That there were different road surfaces, we had different weather conditions, and we collect not only with cameras, but also with the LiDAR information. And this is where it was collected. It was collected in in a place called Kura, which is 4 hours from Sydney. And for Transport for New South Wales, it was quite interesting place because they have a facility running there where they want to start evaluating this kind of technologies. And we found, for example, some artifacts from the LiDAR information, especially when it was raining. And now just faster here. That annotation was super hard, getting each point in the point cloud annotated as something. It is incredibly hard. I did it with one of my students, and we don't want to do it again. It's a very boring, a very lengthy process. And this one, just to finish, it's a project that we have with Cornell University. I went to Cornell, I talked to them, they were like, we should have a collaborative project. We're doing stuff in self-driving. We have a student coming to the University of Sydney. We created a very interesting data set. We had all the vehicles and the roadside unit traversing that intersection. So we have 3 vehicles, 1 roadside unit. In total, we have 1, 2, 3, 4, 5 point clouds at the same time. It was a huge amount of work doing the synchronization and doing the calibration on all the LiDAR sensors and doing the localization also. As you can see, it looks quite impressive. This paper is about to be published. And what we did was we focused on vulnerable road users. So we collected a lot of information from the pedestrians, from the cyclists, from people, for example, in different kind of mobility, not only cyclists, but also what is it called? The scooters. And we send that, everything we send it for annotation. And the kind of annotation that we obtain, because we have some funding for this kind of project, it is very high quality annotations. And because we have the annotations of the intersections, we can get annotations for each individual vehicle. And I know I'm just talking too much. I'll probably leave it there. So if you have any questions, we have a few minutes.
I have 2 questions for this. One is that how many categories are in the Robotics? Because I know like GT only has 3 or 4 categories, and it uses more than less than 10. So how many categories?
I think we use new scenes approach for doing the annotations. So we have a number, I don't remember exactly the number of categories that we have, but we should have around 10, 9. So we're discriminating between, for example, someone that is in, like, especially the vehicles. The vehicles here, they look quite different from the vehicles in Asian countries. They are like smaller. When we compare the vehicles in Australia to the data sets that we found in the US, the cars in the US are just very big. And all matters when it comes to training AI models, because they only learn what they have seen.
And another one is, like, have you tried like some animal, like automatically annotation, like skill AI? I know there's some method can like automatically annotate, like, or point out data online.
Yeah, we have proposed several methods for automatic annotation. It's good just to start the training process, but it's not good enough just to run a whole pipeline and deploy it from that kind of data that you obtain. You always need, even if it's just for testing, you always need high-level annotations.
Thank you for your presentation. I just wonder how weather condition affects your work, rain, snow, and other conditions.
Well, because everything has been collected in Australia, we don't have snow, right? So we have different illumination conditions when it comes to cameras. Probably lighter, it doesn't matter. This data set was collected during, like, when it's sunny and beautiful, so we don't have any kind of interference. But this, for example, this data set was collected when it was raining. And everything depends on the ODD of your implementations, which comes to the operation of the site domain. So everything that you deploy will have some restrictions. For example, the cards that we use have the restriction that you cannot use it during the rain, because we use LiDAR information. And normally when you have rain and LiDAR, there's a lot of interference. And also because we don't have protection for rain. And we have cloudy environment, overcast sort of here. When it's sunny, when in different seasons. The problem here in Australia is that everything changes, but it doesn't change that much. So it's not like in the US. For example, my colleagues from Cornell, they were saying, oh, we have a data set that, you know, when it was snowing very hard and when it was like sunny, we don't have that type of environment here. But yeah, we try to do it as much as we can.
All of your work, you use ChatGPT for generating these prompts used for the basic language model, more or less. What do you think about directly using the large language models for the detection and also the semantic context, semantic information extraction?
That's a good question. So yeah, this one was when ChatGPT 4.0 was the latest one. So that was quite some time ago. The thing is now these large language models are advancing so fast and they are so accurate that is very, very impressive. The first question was about if we use ChatGPT for anything else but just getting the prompts.
Have you tried actually just putting the
We did.
Yeah.
We did at that time. We haven't done it again because we have finished with that project, but we did it. And it was not as great as we thought at that stage. The visual language models that we were using was the one from Google. And it was okay-ish, and that's why we have to combine the prompts, saying just cassawari, you know, black emo, just detect something else, just to make sure that we can actually capture the animal itself. But if you have multiple animals at the same time, it's going to be very confusing for a VLM. We are actually doing some experiments now with visual language model and large language model on how to interpret the environment. This is very close to the end-to-end autonomous driving, where you have just the camera information, and then at the end, you only have the control of the vehicle. It is impressive the way some companies that are doing that, especially I think Wave in London is doing something very similar. But it's tricky in the sense that regulating that is hard because it comes to the question, who is in charge of which module or what actually happened when you have an accident? If it's just a lot of features being combined inside, it is very hard to track what happened in terms of an accident.
Just wondering what type of method you have used to control
Yeah, the controller is just Stanley control. So it's not a very fancy controller. We're not using anything like related with ML. It's just a very simple Stanley controller. We don't use MPC. MPC has the disadvantage that it takes very, very long time in order to do the compute. So we're using just a Stanley controller. Yeah, yeah, because MPC is usually, yeah, you will have to go very, very slow.
How did you make sure that the problem can
There are a lot of restrictions in the controller. And those restrictions have been somehow hard-coded in the, yeah, in the document. Yeah.